Hello everyone. In this short video, I'm going to show you how to do Makefiles and how to use Makefiles to organize compilation of your C programs in Unix environment. So what I want to do is I'm going to go through a few slides and then I'm going to show you one example in Ocelot, and that should do it. So let's go through my few slides and introduce what Makefiles are. Basically, as I said, Makefile is a very simple way to organize compiling C programs. They have a lot of other applications, but I'm going to talk about only compilation because that's the focus of Makefiles in this class. So let's imagine you have a C program like this. You have a main function inside a file called hello-make.c. In the same directory, you have two other files. One is called hello-func.c and hello-make.h. The files with extension .c are called C source files, and the files with extension .h, which sometimes exist, sometimes don't, are called header files. And when you create header files, like for example hello-make.h, you place some declarations and some other constants and, let's say, global or external variables in it, so that you can include that header file in other files and save some time. So header files are just to avoid elongating the C files. Basically, you define a bunch of common declarations and constants and external variables in them, and then you include them at the top of other C files when needed. So I'll show you an example of hello-make.h later. Let's quickly take a look at this program. In this program, I'm going to call a function called myPrintHelloMake. And as you see in this file, I don't have any function of this name. So in order to define this, you need to, let's say, have it somewhere in your program. In the same directory as hello-make.c, I have another file called hello-func.c. In that file, I have a definition of myPrintHelloMake, and as you see, it has a very small body. It just prints hello Makefiles, and it returns immediately. It doesn't do anything. And also, for this hello-make.c file to see the function defined in the other file hello-func.c, we need to declare the function. Declaration means something like this line, which is basically the first line of a function. Whenever you want to make one file or one function in a file see another function in another file, you need to declare that function so that the compiler knows the definition is in some file somewhere in the same directory as the current file. So basically, the first line of myPrintHelloMake without all of these curly braces and the definitions are all stored in one line, followed by a semicolon, and all of this are inside a header file, which is called hello-make.h. We didn't need to have this hello-make-file.h. We could have put the declaration, that single line, on the top of the definition of the main function in hello-make.c. However, this is the etiquette of doing this. The declarations and macros and constants and external variables, they all go in one single file, like hello-make.h, which is called the header file or include file. Let me erase all the annotations. I'll show you one more example to clarify things further. But as you see, I'm including hello make.h on top of hello make.c, which basically adds a declaration of my print hello make at the beginning of hello make.c, and this way this function is now defined and declared in the eyes of compiler GCC. Now, let's say this is a program you have. Basically, you have a bunch of C files and H file, a header file. How do you compile it and run it? If you want to use GCC, we will do it this way. The GCC command will call the compiler, and then -o hello make enforces GCC to call the executable of the program hello make. Otherwise, if you don't put -o hello make, it's going to call it a.out. I showed you an example before, and then you would basically place all the C files you have, which is in this case hello make.c, hello func.c, followed by -i and a directory of the header files. This is not L, this is capital letter I. And basically what this does is it tells GCC that if you're looking for includes or header files, check out the directory dot, and directory dot means the current directory. So that means if you want to look for header files, just look at the current directory and you'll see the header files. Remember, we had one header file which was called hello make.c. Now, if you want to see more details of GCC command and all the flags it has, you can check out this hyperlink. And we don't really use a lot of other flags. I'm just going to mention a few of them. For example, -w, the lowercase w, will hide all the warnings when you do the compilation, or -g will keep the tables of GCC for the debugging purposes, for GDB execution. You will learn about GDB in this module, in module 2. And what else? Probably this is all you need. Maybe -lm. -lm is used when you have any function that is defined in a math.h library. For example, if you want to use the sqrt for a square root or POW for power, you need to use -lm flag for GCC. That's a weird, GCC flag. I don't know why they design it this way, that for any math function you need to include -lm, but anyways, that's how it is, and you need to learn it. So this is how you normally compile if you want to do it without Makefile, if you do it by hand. Now the question is, then how do I do it without GCC? Is there a way that I avoid all of these long commands? Like, look at this line. This is too many characters for a single compilation. Now imagine you have a bug in your program and you want to fix it, and you keep changing things and you have to compile it again and run it. Imagine if you want to just write down the whole thing every single time you want to test your program. It's going to be a big headache. So that's why we are going to use Makefiles to make things easier for compilation. How does a Makefile look like? Basically, Makefile is a simple file with no extension. I know this sound weird because you're used to having files with extensions. For example, a.c, a.pdf, a.word, pptx, a.doc, a.docx, any extension that you can think of. We were used to having extensions in, let's say, Windows, for example, but in Unix, you don't really need extensions. Extensions are basically kind of useless. They usually don't use them by they don't get used by the operating system as extensive as, let's say, Windows. So you just need to create a makefile with this name and no extension in the same directory as other files you have for your program, like hello make.c, hello func.c, and the other one, which was, I guess, hello make.h. And then you basically you create this file, makefile, and inside the makefile you write down this. This is a very simple one. This is not the one we're going to use later, but this one is going to basically compile the program for you, and you just need to write down the command make instead of writing the whole command gcc-o hello make.c, hello make. Hello make.c, hello func.c -i dot. Instead of using the whole command, you basically call, write down make. I'll show you an example instead of writing the whole GCC. Now, what was the purpose of doing that? Basically, the first purpose of using makefile is to simplify things, and instead of writing a long command, you just write make. The second purpose is that any changes in C files may result in compiling and making the whole program. That's not very efficient. For example, if I have 20 C files and I only change one of the C files, then I don't want to compile all the 20 C files. I just want to compile one of them and then build my program and then run it. So in order to do this, in order to only make the C file that has changed, not all the C files, we are going to use makefiles. This makefile is not going to do it. The makefile we use for the sake of efficiency in compilation and for organizing in this class would be something like this. It looks a little bit scary, but it's not, because of these macros, the capital letters of macros, and all the special characters that you see here that make it look a little bit scary, but it's basically almost always the same syntax. You just need to copy it from one programming assignment to the other. What it does is it creates the hello make executable file by calling the compiler GCC, using all the header files in the same directory, which is basically hello make.h. And anytime that hello make.c changes, it compiles it to create hello make.o. Anytime that hello func.c changes, it compiles it to create hello func.o. And then every time you run it, every time you call them, every time you type the make file, the make command and press enter, it's going to execute this command and basically run GCC and create an executable called hello make. That's hello make without any extension. If there's no changes in hello make.c or hello func.c or hello make.h, it doesn't compile it, and basically it says your executable is up to date. You don't need to change anything. Now, a few points here in this file content, in this makefile. Please note that this space is a tab. Don't use white spaces, otherwise it doesn't work. And this is a tab as well. So right before the commands, we use tab. That's basically the way it works. And if you want to know more about makefiles, I don't want to make this video very long. You can just click on this hyperlink and read more about it and see for yourself what the macros are and other things. We really don't want to do that. We just want to just use this as a body of a makefile or similar to this with a few changes for each assignment, and use it to organize the compilation of the programs that you write. Now let's see a very quick demo. Let me keep this. Give me 1 second. What I'm gonna do is, first of all, I have already opened my WinSCP. If you're in Mac, then you can use CyberDoc. And here you can see my WinSCP on the left side. This is my own computer right now, sitting at home, enjoying my coffee and getting connected to Ocelot. The right-hand side is Ocelot. Let's double click on COP4338, then SV23. Then I have created a makefile example. You can create a makefile for a directory this way, new directory. Already built my own, and I have already placed a few things in there. Let me delete some of these. I'm gonna delete all of them to start fresh. And it says what? Deleting. Okay, we try. All right, skip. I guess it's, yeah, it's already deleted. I didn't need to delete it again. All right. So what do I have in this directory? I have a util.c, the circle area calculator. Let me open circle area calculator. Do you want to reload it? Yes. So this is a Notepad++. This is my favorite editor. I'm going to show you how the program looks like. It's a very simple main function in a simple program. All it does is it asks the user for the radius of a circle, and then after the user enters the radius, then it's going to call a function called area calculator. This function is not defined here. It's just declared on the top. You see the semicolon. I showed you what declaration means, different from the definition, because I'm going to define it somewhere else. I don't want to define it here, so I only declare it. If I don't declare it, I will get a compilation error. And after calculating the area using the pi r square formula, we're going to print out the area using printf. Scanf and printf are kind of opposite. Scanf works with the standard input and keyboard. Printf works with the standard output or a screen. Scanf will scan some variable, in this is radius. Don't worry about the ampersand. I'll talk about this when we talk about pointers. Just assume that you have to write down ampersand, otherwise this scanf doesn't work. And LF basically stands for long float, and this means you want to convert the text into a long float, or double, I should say. And the area calculator is going to calculate the area, then I'm going to print the area of this circle is this much. 0.3 LF means I'm going to have a double, which is the area, printed on the screen, and I would like to have 3 digits of precision. That's why I put 0.3 in the placeholder. Then I will calculate the volume using volume calculator. Where is it defined? We don't know. We just need we just see the declaration, and we only need the declaration. And then I will have a printf where I print the volume of its corresponding sphere. So a sphere with the same radius has a volume, and we're going to calculate the volume in this function, and we're going to print it out. Now, one more thing I want to do. I'm going to show you the makefile in a second. Let me show you the makefile first. You open the makefile. Yes, reload it. You will see that I have a similar structure as I showed you in my slides. Basically, there's a tab here, there's a tab here. Here I have CC, GCC. That means my compiler is GCC. I'm going to use -w flag for it, no dependencies because there's no H file. I'm going to make the H file right in front of you so you see how it works and you don't get afraid of making H files for yourself. Then I have the circle area calculator.o as the object files and util.o. Basically, I have a same names with .c in my directory, so I use the same names .o for my object files. And then I have the GCC command once here, and then here is the name of the executable. Later, for different assignments, I will tell you like change the executable name to a different name in the assignment specification. You need to change this. So calculator is the name of the executable that I will get by compiling my program, by making this project, or by making this program, I should say. All right. So let's see why we need header file. We don't really need it. It's recommended to have it. Let's open circle calculator. As you see, I have two declarations, and as I told you, declarations are usually placed in a header file. And then let's open the util.c, where you can see the definition of both of them. This is the area calculator, which basically implements the pi r squared, and pi is basically m underline pi, which is defined in this library. And volume calculator will use 4/3 pi r cube formula for the radius of a sphere. And I have the definitions here. I don't want these to stay here, even they include stdio.h. So what I do is I cut them. Pay attention to this, and I will say number sign includes, and in double quotation, no more angle brackets. On double quotation, I will put calculator.h, and I close the double quotation, or save this file. Then I go back to WinSCP, and I right click here, new file. I'm going to call this calculator.h. And here I will paste what I cut from circle area calculator.c. So now, if I save this, what do I see in the WinSCP? I see three files: util.c, circle calculator, circle area calculator.c, and calculator.h. Now let's update the makefile so it uses calculator.h. So the dependencies are now calculator.h because I have a header file. The flags should include -i dot, and later you will use gdb. So let me add the -g for you here. This is just a flag. You will see the details of gdb later. And that's pretty much it. I can easily compile it using Makefile now. So let me save everything and open PuTTY. All right, let's put the host name ocelots.aul.fiu.edu. Enter. Login as my username, my password. Let's make it a little bit larger so you don't have any problem seeing this. Change it to 18. Apply it. All right. So let's clear everything. What? Okay. Now cd cop 4338. I'm going to navigate to the same directory that I was showing you in WinSCP, sp23/makefile example ls. And as you see, I have util.c, I have makefile, I have circle area calculator.c, and I have calculator.h. Because I have makefile, let me show you makefile, cat makefile. This is the makefile I did 1 minute ago. Then I will use make, and look at this. It will automatically execute all of these commands. It executes the first command because it wants to find out, it wants to compile the circular area calculator.c separately. It will compile util.c to calculate util.o, or to generate util.o. And after it has all the object files, it's going to build them, and it's going to put them together to create calculator executable. Now, if I say ls, I will see different files. I will see this executable. That's all I need. But I see some .o files, which I can get rid of by saying remove all the .o files. If I ls now, I don't see the useless. They're not really useless, because I'll tell you why they're not useless. But I don't see the .o file. I only see calculator.h. If I want to make it again, then it will do all the compilation again. Why object files are not useless? Because if I want to make the third time and I don't remove any object files, it simply says calculator is up to date, because it looks at the object files and say they're there, and there's no change in the C files after the O files are generated. So it realizes that I didn't change any of the C files, so it doesn't waste its time, and it doesn't compile again. So it doesn't recompile. So keep the .o files in place when you're doing a lot of debugging and you're doing back-to-back compilation processes. Now, let's run it, see if it works. The name of the header executable was calculator. So we say /calculator, enter, and that's how you run your program. Please enter the radius of a circle followed by a new line, let's say 12.34, and it tells me the area and tells me the sphere, the volume of the sphere and the area of the circle. So that's how things work using Makefiles. So that's pretty much it. Let me emphasize on the fact that here we have tab, not white space. And for the assignments, you only need to change the header file name, the .o files, which are going to be the same name as your .c file. It can be 2 files like this, or it can be 20. Doesn't matter. If you have 20, just list them here. Just go further. Then you can use this makefile for all of other programs that you might have. So with that, we're going to end this meeting. Thank you.